Before we start, I would say a couple words about this event. So we started different activities, research and development and educational activities in several points, in several locations. First is, of course, Electrotechnical University. Second, in 2 universities in India. And this is the time to have a joint seminar. We will have it once per month. And today we have 3 talks. First from our side, from LT. It will be given by Andrei Gavrilov, and more 2 presentations, 2 talks from Indian side. There we have 2 teams of students. So the time slots are like 15 minutes for the talk and 5 minutes for the questions and discussions. So, and Natasha will be kind of a host of this activity. Yeah. Thank you.
Yeah,
let's get started.
Dear friends, let me clarify one thing before Andrei starts the presentation. Andrei, about questions, is it possible to ask questions during your speech or maybe after your speech?
I think it will be better to ask questions after my speech.
Okay, dear friends, please type your questions into the chat, and we can discuss it after Andrei's report. Thank you so much, Andrei. I think you can start your presentation.
Yeah, okay. The topic of my report is non-invasive heart pulse detection. So to begin with, I want to define some terms. Heart rate is a known human parameter, which is calculated as an inverse value of RR interval. The RR interval is the interval between 2 peaks on the pulse wave, which are called R peaks, as shown on this slide. The global task is to estimate heart rate variability in a non-invasive way. The process of measuring the pulse using data on the filling of human blood vessels and using data about skin tone changing, skin color changing, is called photoplethysmography or PPG. This task can be divided into 2 different tasks. First is to estimate pulse with wearable devices, such as smartwatches, and another one with a regular camera. Pulse calculation is a popular task for monitoring stress and monitoring human conditions. Such information can be applied in different parts of our life. For example, data about human stress can be help for planning employees' rest, and as a result, increase the productivity of the employee. Okay. We can share 4 main stages in solving the problem of estimating pulse rate and pulse wave. They are first of these tasks are first task is search the region of interest on the skin of the human, and then signal processing, pulse measurement using data using the signal and the data about peaks on this signal, and selecting the most accurate regions of interest where we get the most accurate results. So on the slide, you can see an and compare the processed signal from our program of estimation pools. On the right side of the slide, you can see red, green, and blue lines. Each line is a signal from different point of interest, and the black one is real pulse, which we get from a heart rate monitor. The main difficulty in this task is signal processing to obtain a pulse wave. Therefore, state-of-the-art solutions for obtaining this pulse wave from video are considered. We have two main approaches of estimating pulse wave. They are a signal processing approach and image processing approach. First approach consists of the averaging RGB component of the region of interest and filtering the signal. The second one consists of different machine learning methods for estimating pulse wave. All considered analogs and implementations were tested on the UBFC dataset, but in our case, we use our own data with more than 30 videos of different people. You can see some examples on the slide. Okay. The considered methods we can see on the slide, two methods are used. Deep neural networks, for example, BMI and efficiency-FIS network, and they get the most accurate results. Such a mean absolute error about 0.65 bits per minute. The another approach were signal processing, and this analogs shows us not so accurate results with error more than 4 bits per minute. Okay. On the slide, you can see our approach, the scheme of our implementation. In our solution, we collect 8 seconds of sequential data from which we extract an average signal over an area with a radius of 3 pixels, which also called region of interest. In our approach, we estimate pulse only in 4 points on the forehead and the cheeks of a person, but we get 468 different points of interest from a human face using MediaPipe library. Then the signal of each color at each region of interest is filtered and processed by different methods independently to analyze which method will be better when we get results, when we get the mean absolute error of the measurements. After processing the signal in all presented ways, the heart rate is calculated for each of them, and the mean absolute error is measured. We use estimation of heart rate by peaks count on our window, on our 8 seconds interval by error interval, as shown on the first slide, and by spectrogram using Fourier transforms and the Welch method. Now we can see our results on more than 6 hours of continuous data of different people from our data set. Our results at the moment show a fairly large error, about 11 bit per minute, using estimation by error interval. But in some articles, there are exactly the same error as we have for the methods we use. I think the error is caused by more complicated data set that we have because of moving persons on the video. The rest of the data sets use simple conditions with a monochrome background, and it causes more accurate results, I think. So thank you for your attention, and I'm ready to ask to answer your questions.
Thank you for your presentation, Andrei. Please look at the chat. We have 2 questions. I will read them. All people have different pulse. How can the system be adapted to the individual?
It's a difficult question, I think, because our signal processing methods use only constants filtering, but as I say about the tasks in this problem, we should select the most accurate points of interest and the regions of interest where we get the most accurate result. We have no any approach to do this, but we try to cluster points with the same heart rate and use the most the biggest cluster as the cluster with the most accurate result.
Okay, thank you. I have one question in continue. Maybe we can use feedback from our system for adaptation.
We are not using machine learning methods now, but we are planning to do this, and it will be possible to get some information from the human to get more accurate results. But now, any parameter we are using, we cannot predict these parameters, or a human cannot give us these parameters to get more accurate results in our calculations.
Okay, understand. Thank you.
The second question was about what the national challenge for now, and what are the hypotheses to solve it?
I haven't seen any implementations for signal processing using different machine learning methods, such as support vector machine or different gradient methods. But I think deep neural networks are the universal approximators, so we can use it to estimate heart wave, pulse wave in any condition if we have a lot of data in different conditions.
Does it mean that we need to collect data from many of human, or it means that we need to observe one person for the long period?
We need very different videos from different people of different ages, skin color, and in different conditions, such different light and different maybe different in other conditions.
Different parameters, right? So, but this is sounds like chicken egg problem, right? So we cannot classify conditions and human states before we collect data and label it somehow, right? And on the other hand, we try to classify signals we have, right, to understand different conditions of human we observe. So it's kind of tricky. So is there any ideas? Yeah, is any ideas to solve this kind of problem?
We have a lot of different parameters which we cannot predict and cannot manipulate with it. So one of the methods we were using were factorial analysis, which the goal of this method is to estimate different variables in our signal. Using this method, we want to get only the component of our signal for pulse wave, and another components will be just dropped, I think. But this doesn't work in our case. I think we can use now deep neural network as a black box to analyze firstly the region of interest, not the signal from this region of interest.
Okay.
Andrei, thank you for your questions. Sorry, dear friends, we have no time for this report to ask Andrei, and we need to continue. If you have some additional questions for Andrei, please type them into the chat, and I will ask Andrei to answer these questions in chat also. Now I want to ask Grusha to join this screen sharing and to start their presentation. The next report will be about eye capture for motion classification.
Yes, ma'am, I will just share.
We can see your PowerPoint screen. Yes, and we can see full screen mode. Thank you. You can start.
Yeah, good evening, everyone. My name is Taran, and I'm joined by my colleagues Grusha and Nikhil. So our main topic is to determine a person's emotional state from their eyes. So what we'll be discussing today for today's seminar is the problem statement, first of all, and we'll also discuss the current research that we have come up with, as well as our current development research. All of our results which we have accumulated till now. We'll also provide a small demonstration using the slides itself to showcase what exactly our efforts have produced right now. And we'll also discuss the future development plans that we have and what other points we can be taking to get a more accurate result, as well as a more multimodal approach. So even for that, we will try to see how we can go towards a multimodal approach. And then we will, of course, list our references. So yeah, the main problem statement that we are trying to solve is to determine a person's state by their eyes when they work at a computer. So a lot of us, we might work in a in a situation where we are in front of a computer screen for nearly 11, 12 hours at a time. And so what we want to do is identify the person's emotional state, whether they are happy, whether they are sad, whether they are whether they are more angry, or whether they're bored, or whether there's any kind of any sort of disgust or any of those emotions in their video feed. So we will take a webcam's video feed and we will use that as our main input. And using that, we will identify what exactly the emotional state of the person is. And we are currently starting off with 6 different emotional states. So the main part that we want to use is the pupil diameter. So why the pupil diameter is because when a lot of researchers have conducted experiments between various parameters of a human, such as blood volume pulse, or skin response temperature, and pupil diameter, and heart rate, all of the experiments yielded one conclusion, and that was pupil diameter with respect to the eyes is the most has the most potential for identifying the emotional state of the person. And of course, as we all know, pupil diameters and the constriction or the dilation of the pupils, they provide a lot of valuable information regarding the emotional state of the person. In fact, it has nearly become common knowledge that the pupil dilation or constriction is directly linked to the emotional state, whether they be happy or whether they are sad, or whether they are in a state of processing some sort of emotion, or whether they are processing some new information. All of this can be directly conveyed from the pupil diameter. So a lot of other research teams have also come up where they have used the pupil diameter to identify the onset of diabetes in a person and what exactly the stage that they're in. And medical approaches have also yielded very significant positive results. The pupil will dilate whenever it is more in a state of concentration. So if the human is in a state of concentration, or whether if they're in a state of elation or joy, the pupil will dilate. The constriction of the pupil will occur more when they are in a state of anger, or whether they're in a state of sadness. So this research has been fortified by the research of Arch and Barrett. They, of course, as I said, they have conducted their own research. And when they found that they can measure all of these parameters and to identify which exactly yielded the best results, they found that pupil diameter was the best among all of the tested parameters. So let's just move to the current state, what we are in, and what exactly we have achieved till date. So the first system that we have is a gaze tracking system. So this is combined with eye tracking, but eye tracking is directly utilizing a Haar cascades model that is built into the OpenCV library. This directly just draws a simple rectangular box around the eyes as soon as it detects it, and it uses built-in OpenCV libraries. It does not have any specific data set, and it does not get into any sort of landmark detection. So the second system is the gaze tracking. So what this uses is the OpenCV libraries as well for all of the basic OpenCV functions, such as to get the video feed from the camera and to perform processing of that. But it also uses something called landmark detection, which is built into Python. So what landmark detection does is that it identifies points in the entire video feed, and it determines the exact axes, so whether it is x-axis or y-axis, and it assigns it to us on a graphical plane. So if all the points can be mapped, then we can identify where exactly the pupils are. And then we can say, okay, the pupils have moved towards the left or towards the right. So based on this, we can say that the person is looking to the left or looking to the right. So this landmark detection is built using Python, and it is integrated with OpenCV methods. The other system that we have is a fully facial detection and emotion classification model. So this is an open source system, and it is similar to the previous system, as in it uses OpenCV built-in libraries to capture the faces. But once the face capture is done, they use an FER 2013 dataset, which has 26,000 images for training and nearly 8,000 for testing. They utilize this data in a convolutional neural network, and using that convolutional neural network, they can predict whether the person matches the classification of happy or whether it is classified more towards sadness or joy or anger. And that is a complete OpenCV based system. It does not have any specific data set for the capturing, and it just uses the simple face detection built into HAR cascades. So this is a demonstration of the gaze tracking system, and it can also react to pupillary movements in real time, and it even to rapid changes. So if I suddenly move left or if I suddenly move my pupils to the right, it can detect that change and it can reflect that change very quickly. I'll now hand it over to Grisha to talk about the eye capture as well as the challenges involving eye expression classification, emotion classification.
Thank you, Dharani. As we were trying with those, we faced a lot of difficulties. One, that we didn't have any preset recorded data that give us an exact measure of the pupil diameter to classify for so-and-so emotion. A detailed research related to the medical field had to be done for that, which we weren't accustomed to. And we faced a lot of problems in coding areas as well. So starting again, we thought we would rebuild our whole model into just a binary classification for now, and then try for a positive and negative emotion. So we thought that for a given set of photos, human will classify emotions, and SVM using support vector machine, it was found out that it was 85.9% accurate. So support vector machine classification problems were based on quadratic optimization of the problems. So what we are trying to do is we are trying to collect a different set of data set all over. We are trying to build our own data set. Crop the eye images, like for happy faces, like we're going to take some 1,000 happy faces, crop the eye images and train them, and a sad image, basically a negative emotion. So we are going to classify them as -1. Later on, what we thought was, after adjusting the data set for binary classification, as one class was selected for happiness, all the happy faces were classified as +1, and all the non-happy faces we are going to classify that as -1. And the result comparison should be of simple binary classification. The next class is selected, and the positive and negative examples are reclassified for training. So the mean scores for all the 6 binary classification will be recorded based on that. And once we are successful for the binary classification, we thought we are going to move to the multi-class comparison and then integrate CHI on it. So the processes which we are going to have is, first we're going to capture the images, and then we have to image pre-process it, then split it into training dataset and testing dataset. And then we are going to pre-train the model and then fine-tune the model and then predict the dataset. I request Nikhil to take over now.
Sorry, we couldn't hear anything.
Wasn't I audible? Hello?
Hello, yes, we can hear you, but Nikhil, we couldn't hear.
Should I explain it once more?
If I correctly get, you ask to your colleague continue speech, yes?
Yes.
But we couldn't hear him.
I think he has a little bit issue. Nikhil?
Maybe some troubles with microphone.
Maybe.
No, so Grusha, if you know this material, you can provide it this for us, right?
I think Grusha, Nikhil is not actually logged in.
Okay.
So just brief what you have done there. I think you can continue.
Okay, so no problem. Yeah, so as I was telling, we are going to take in a different set of data sets, and then we are going to train them. So we are going to give a weight for each node for any particular problem, and then we are going to pre-train the model with 1,000 of categorical images. As I said, we are going to build our own data set in this case. So as Julia ma'am suggested, we build a data set of 30,000. We thought we are going to cut short it right now since it's for binary classification, and then go for a 2,000 base data set right now, 1,000 for a positive emotion, and another 1,000 for a negative emotion before moving for a multi-model classification.
So this is basically the formulas that we are using for our accuracy and precision calculation. So as I mentioned before, we have focused on 6 primary facial expressions, which are anger, disgust, fear, happiness, sadness, and surprise. And for all of these 6 emotions, for training and testing performance measurement, we are basically using a confusion matrix. So confusion matrix is built of the 4 main slides, which is true positive, true negative, false positive, and false negative. And true positive is when the prediction or the classification is positive and the actual emotion is also positive. So if it's true negative, then what our prediction and classification is actually right, and whether it's false, that is true negative. So is false positive, what it is basically the prediction does not match to the actual emotional state, and if it is portraying it as positive falsely, that is false positive. So false negative is when the actual emotion is positive, but it is displaying it as a negative. So the accuracy formula is TP plus TN by TP plus TN plus FP plus FN, which is basically true positive plus true negative by true positive plus true negative plus false positive and false negative. Our precision is basically the ratio of correctly predicted positive values to the actual total number of positive values. So as I just mentioned, the total number of positive values will be true positives and false positives. So it will be true positive over the sum of true positive and false positive. And recall is very similar to precision. That is the proportion of correctly predicted true positive, true false negative, and false positive. So it should be TP by the sum of false positive and false negative. So our future developments, what we want to do is, once the emotion classification part has been perfectly defined, and once the video capture can be accurately identified, what we want to do is have the emotion classification by the machine learning model as one side, and then we want to have a human come in and say, okay, the actual prediction was right, or the actual prediction was wrong, and this is the actual emotion that I'm facing. So in this way, the coevolutionary hybrid intelligence theory will also be integrated into the system. And what this will do is provide a much more accurate system. And what this will also enable is, it will enable a level of transparency and trust in the system. So if we can trust that the system provides a more accurate result and a more trustworthy result, then we are more inclined to utilize and provide value back into the system. So that is where the involuntary behavior comes in, which is the machine learning prediction model. And the voluntary behavior consists of our human providing some sort of survey, basically, on how exactly the classification was done. And both of these will then contribute together to build a more accurate system.
We had actually several ideas for implementing CHI. One of the idea was, once the prediction is given, we are going to ask the user to tell if the answer was satisfied to him or not. based on his answer. Suppose if it is yes, then the loop will terminate. If the answer was a no, then it will go back to the step where the predictions were made, and we are going to ask the user to enter the right answer, and that answer will be stored in the data set for further training. Now, to store that data set, we were thinking of creating another new data set apart from the training data set, and then storing the values there for further use. And if at all such similar entities are encountered in future, it is going to compare the values whichever the user is going to enter with the new data set. If at all those values are present in the new data set, those answers would be given more weightage than the ones which are in the training data set. If at all the values are not there in the new data set, we thought of coming back to the training data set and then giving the answer from there. This is one basic idea we have for implementing CHI, which will require a little bit of coding and other theories involved in it. We have to do a hit and trial method. So for now, we thought we are going to build a binary classification and then going to implement CHI in that. Thank you.
Thank you.
for your
These are the
presentation.
references that we've used, and thank you. If
Thank
any
you.
questions are present.
Yes, we have questions in chat.
Okay.
Maybe I ask Anton to ask by voice. Is it possible?
All right, sure.
Thank
I
you.
have two questions. First of them is that in the beginning you have said, but I kind of missed that some words about the accuracy of existing methods that can perform the classification of emotions. I thought that you have said this. Am I right?
Yes, sir.
And can you please share these existing accuracy? Yes. What is the accuracy that is might be expected?
So from the open source system that utilizes convolutional neural network, we typically saw an accuracy which is in the range of 65 to 70% on an average. Because one thing was, it was only usable when the person looked head on at the camera, and it did not react well to any changes in the light, or it does not react well to any sort of changes from the ideal condition that it has trained for. So it is a very simple system where if it matches a detection that is present in the FER dataset, it directly correlates those two.
Mm-hmm. Okay, I get it. And another question is, are you going to develop an end-to-end machine learning system, or you want to develop something that would somehow decrease the dimension and maybe distinguish some features on the face that would allow to find the emotions with machine learning methods?
So the primary concern that we have is utilizing the eye alone for the capture in the preliminary stages. What we are looking for is a multimodal system that utilizes not just the eyes, but the entire facial features and all of the facial landmarks to be utilized to build a more accurate system. But that is after we can build a confident system based on the eyes alone.
Mm-hmm. Okay, I see your point. The only thing that I have to say is that you will face the same problems as we did with the light conditions and so on, some weird artifacts that might appear on the face and that are like unhandled for human.
Yes, it is highly likely that we will. So
did your research involve detecting of a pupil, the diameter of the pupil? Because we are facing problems in getting the pupil diameters, like the exact values for each emotions, because any paper we read, at the conclusion it said that we couldn't have a normal reading for it. Like they also specified that taking the readings of only the pupil diameter is very inaccurate to provide an exact measure of emotion for an individual, because it varies from individual to individual, the diameter the pupil dilations and everything. It varies from individual to individual and from a category of people to another category of people, like a set of region wise.
I see. All right, thank you.
Thank you for your presentation, for great discussion, but we need to go on, and I want to ask colleagues to start our third talk, voice analysis for emotion classification. Yes, I see one microphone turns on.
Good evening, everyone. I'm Ishwari. And with my colleague Anjan, I would like to start a presentation, which is based on voice analysis for emotion recognition. Yeah, we are gonna talk about our introduction and our problem statement, audio analysis, audio processing, audio feature extraction, emotion extraction from text, and result, and then demo, and then future development and research, and the references we have did for our research. Yeah, as we know that emotion recognition is an important feature of our daily life. It is very as a human we can easily identify our emotions, but here we have to train our model from using different machine learning approaches to recognize the data and to recognize the different emotions of a person, such as happy, sad, neutral, fear, and disgust through the voice channel. And here there are basically two features. First one is acoustic and the second one is lexical. Acoustic is the sound properties like pitch, tone, and jitter. And then in lexical feature, we use the different vocabularies. When we use like happy, we will be like, it's amazing. And when we are sad, it will be like it depressed, guilty, and everything. And then like in lexical feature analysis, there is one thing we have to extract the text. We will use the text transcription here. And then there are numerous ways of processing the audio from the raw audio waveform. And then we have direct human-computer interaction. And here we use, we have major challenges faced in emotion recognition. There are so many data sets such as test data set, save data set, RAVDES data set, IMOCAP data set. The most commonly used data sets are RAVDES dataset and IMOCAP dataset, as we have seen in many papers. And next, our problem statement is we have to determine, our problem statement is to determine our person's conditions through the voice analysis using co-evolutionary hybrid intelligence. That is direct human-computer interaction. We can usually we can record the audio from phone or phone calls or phone conversations to monitor the person's condition and then critical condition, and then train our model whether the person is in which state of emotion. We use this by recorded voice can be represented in the wave format, and then this can be predicted to like high and low frequency. Like when person is excited, he will be having a high frequency of voice, and like that. And we use different phrases, and then in audio processing techniques, audio signal processing is basically used to convert between analog and digital formats. Analog processors operate directly on the electrical signal, and whereas digital form processors operate mathematically on its digital representation. And next, noise control. Here we reduce the unwanted sound, and then to add effects. Adding effects is usually used in music, and then we will boost the frequency of audio ranges. And then yeah, it includes even the cleaning up of background noises so that we could get the clear audio to get the clear audio so that we could predict our emotions easily without any noises. And then waveform audio files can be converted into different waveforms and studied and analyzed for the feature extraction. There are different types of audio processing. Compression is basically used for reducing dynamic range of signal, and then equalization is used for increasing or decreasing the levels of different frequencies. And then expansion is used for expanding the dynamic range of the signal. Localization is used by the listener's ability to identify the location of sound in direction and distance. And next, I would like Anjan to continue the audio feature extraction.
Yes, myself, Anjan S. Just a second. Yeah. Is the screen visible correctly?
Yeah.
Just more fun. Sorry for that. So yeah, in the audio feature extraction, basically what we came across is the if we talk about the accuracy and flexibility of the model, so we would need multimodal integration. So extraction of features from the audio is basically done by analyzing the audio file by converting or representing it in the .wav form, waveform basically. So by analyzing the waveform, like basically the pitch of the wave, if we plot it in the if we plot it against the graph. So by analyzing that, we can extract emotions, or we can categorize emotions based on the numerical values or the shift in the graph which we see. And extraction of emotions from the text is basically done by observing certain words, like whatever we speak, or the text which is converted from the audio will contain multiple fillers and other non-essential elements for the emotion extraction. But after we apply certain techniques, we can get whatever the certain words which we need for extracting emotion. So this is about audio feature, like the feature extraction stuff. And this is the current system which we have developed. Basically, it's a 50% now extraction of emotion from the text. So here we are considering the Twitter dataset. So whatever the tweets which will be available in the Twitters and the tweets, so that text is collected in a CSV file, basically Excel file, and they're mapped against certain emotions. So after that, we will be applying certain cleaning text cleaning techniques from the NLP, and dividing certain statements into words, and then those words will represent certain emotions, and we'll feed those words to train our model, and we'll test that against this user input. So this is how the actual current system which we made is working. That I'll show the demo in just another slide or two slides. So this way, our model will yield an accuracy of about 60 to 70%. So, and our future thing is to develop our own data set by considering what are the communications which we do in real life, or what are the statements which are present in a book or in newspapers which we read day to day. So yeah, this is the result, and snapshot of what are the result which we get. So first, in the first output, so the system will ask us to speak and to stop, like it will provide 5 seconds of gap, and that the audio file will be stored in .wav file. And that WAV file is basically loaded into the program, and then it is converted to text. And from that text, the further process will be done. So the statement or the audio which we spoke in that audio file was "I got the job." So emotion which is extracted from that statement is joy. So it is, I guess, accurate. And down is the accuracy, snapshot of accuracy. So as you see, it is yielding around 60 to 70% of accuracy. And then, yeah, I'll just show you the demo. Yeah. So yeah, this is the actual program which we have developed. So here we'll be importing whatever the modules which are required and the algorithms and train test split. So this is the data set which we are using currently, and it will be split. It will be stored as a data frames, and this is the structure of the actually the actual data which is present. So there is two columns which are emotion and text. Text is basically the tweets, and emotions are whatever the emotions which are mapped to the actual statements. And then these are the count of statements which are mapped to the certain emotions. So basically, if the emotion is joy, then we have 11,000 data lines. And this data set contains around 34,000 entries of data. And this is the part where we apply cleaning, data cleaning and tokenization or some like that. So the remove user handles will just remove, basically cleaning up of data is done here. After cleaning, so this is the actual text which is present, and this is the clean text. And then we'll split it into train and test and feed it into the algorithm. So this part is recording an audio into the file and then considering it again and converting it to text. So this is the output of the converting part. After that, in this part, we are displaying the output. And these are the values which are got by considering the input and the train test model. So, and these values are basically mapped to these emotions, which are anger, disgust, fear, joy, neutral, sadness, shame, and surprise. So this is one demo. And we also came across emotion extraction from audio. So this is still in process. So what we found was we are using a RavTest dataset here. So there are certain audio files which are spoken by actors in a bunch. And this is the dictionary of the emotions which we are considering here. So this is the actual data set. It is considering the whole data set into a for loop and iterating through it. So after that, this is the whole output of the whole data set, whatever the emotion it contains. So we are actually in the half process. So we have to again train our model and then actually test it against the user input. This is just classifying the data set which is present. So after that, the future development and research. So our plan for the future is to gain more knowledge about emotion extraction from the audio. Like we have a pretty good model of the emotion extraction from the text, but we are still basically lagging behind in the audio emotion extraction from the audio because there are too many models and we're concerned about the accuracy and other numbers. So yeah, that one. And to perform additional research on the open source field, because if we have any pre-existing systems, we can implement that directly without any license or other kind of fields to go on through. And to gain more knowledge about the future techniques in the multimodal integration, because whatever the models we have, like emotion extraction from text and emotion extraction from the audio, we have to integrate those both in a very precise manner to get a optimum output. And to gain deep knowledge about correlationary hybrid intelligence in an effective way, and basically have to find an effective way to apply it to the integrated model, whatever the integrated model will be performing. So according to me, like the correlationary hybrid intelligence, just a simple glance of how we are planning to apply is like whenever the model predicts an output, like if it's sad or angry, and if it's not precise. So when we give the feedback, it should go and store into the another CSV data, another data set. We'll create another data set. So another point is we could add logging. Basically, we can create a log file for whatever the output our model predicts. So whenever the log file has to be gone through every time. So whenever the previously given output is again predicted from the model, and if that answer is already present in the log file, then we can just take the input or the output consideration from the new data set which we have created again. So basically from that, we can again reduce the work for the model to go through both data sets. So, and to develop a proper user interface for our integrated model. That's our future development and research plans. And I would like to ask Ishwari to explain the reference sheet.
Thank you so much for the presentation. We see references and I think we can ask questions. Who our speaker?
Yeah.
Yes. Yes, I have short questions. I cannot write this question. Can I ask by voice? Okay.
Yes, of course.
Please show me the slide with program code.
Yeah.
Where we say it about accuracy.
Accuracy, yes.
Yeah. Oh, yes. Please say me, is it accuracy of what? That text X equal text Y, or this accuracy of recognizing emotions?
It is the accuracy about whatever we are testing against the trained model. So that would that's what the dot score would suggest in the model. X test and Y test. So that would be our user input testing against the trained model.
Okay, thank you.
Yes.